All right, let's go ahead and begin. Here you go. For Lab 10, the video was erased. So I'll make it, it'll probably be tomorrow morning before I make it, but it will be posted tomorrow. So if you're waiting on that, I'll get that up ASAP, if you've even looked at that yet.
What are we waiting for? Sorry, what was that?
Lab 10 video. It was erased, so I had to remake it. So I'll post that. I'll make it and post it tomorrow. If you want to look at it, you can. Do what you can without the video. So. All right, tomorrow we'll do a review, and we'll do it right after class. So the same thing as last time we did it. I'll vodcast it. And so if you can come, great. If you can't come, that's fine. I'll send out that vodcast. Yeah, tomorrow's Wednesday, right? I'm right in my head, I think. And the exam's on Thursday. So we'll do the majority of Chapter 8 today. We'll finish it up tomorrow and review. And we might be able to do the review tomorrow in class. I don't know 100%, so I'm just going to say for right now it'll be right after class. If we get to start it before then, great. If not, that's fine too. All right, let's review. We looked at E2. How does E2 like to eliminate, like the hydrogen and the leaving group? The what? It makes a double bond, but how, like, what position, I guess, do they like to eliminate? Like, do they like to be close together, far apart? Huh? Far apart. Usually far apart. So it gets crowded. So remember, it likes to eliminate in that anti-position. So the hydrogen and the leaving group are kind of like the trans. We looked at the cyclohexane. So if, let's say, a bromine's on a wedge, then I want my neighboring hydrogen to be on a dash, to be the opposite. So you're always looking for the opposite. We also looked at the two products an E2 can make. What type of base do you want if you want the Zaitsev product? Small. And then Hoffman would be large, yeah, and bulky. And Hoffman, where does that double bond form? The opposite you would predict. So the least stable side. So it's the lowest degree carbon. The least crowded carbon, if you want. And that was pretty much it for Chapter 7. And in Chapter 8, we learned two reactions. I think you would probably know more than I did. I post on the handouts the Chapter 8 notes, or not notes, but reactions? Yeah. Okay. Let me. Was that under week 6? Yes. Okay. I went ahead and opened the rest of the weeks for you, so you can see those. Let me just show you, because this could help you. And I'm pretty sure I did this for every single chapter that you have reactions. CLC Chrome. It was supposed to be downloaded. I might have to use Firefox. Okay, Firefox it is. Mm-hmm.
Are the answers, the worksheets, online?
No, I can post them. Do you want like 7 and 8? Okay, I'll post those. So it's in our regular lecture course, week 6. So here's chapter 8 reactions, and if I click on it, here's every single reaction that we possibly could go over. Yeah. But I have them all listed in one place for you instead of all over the notes. And then I also put on there, for example, do you see that this is adds an H and a Cl, and Mark means Makarnikov, okay? Or H and Cl, anti-Makarnikov. Anyway, so it has stuff like that on there that'll help you. And then if you look, here are the mechanisms that you possibly might need to know. There, listed for you on one page. Okay, so that's under week 6. Okay, so let's look at 8. Okay, so let's look at predict the product first. What will this add across the double bond? H and a Br. Is this going to be Makarnikov or anti-Makarnikov? Makarnikov. What makes it anti? What are we looking for? Peroxide. So there's no hydrogen peroxide listed on here. So it's going to be the regular Makarnikov. What does that mean? Yeah, you're going to put the Br where the most stable carbocation would form. And then what carbons do we look at to decide? The double bond carbons. So we're only looking at these 2 carbons here. We don't care about the rest of them. They're just there to distract you. Okay? So we have a, what type of carbon here? A primary, and this is a secondary. So where would the bromine go? The secondary. And then what's hidden on the other side? Hydrogen. How could I accomplish this? So this would be like a synthesis. Hydrogen peroxide. How did you know you needed hydrogen peroxide? Yeah, the chlorines at the end, so it's at the least substituted carbon. And what else do we need in there? H and Cl. All right, and then let's look at the mechanism for the top one, since that's one we need to know. Okay, what is the first step? Yeah, the double bond will grab the hydrogen. What happens to this bond here? Where does it go? To the bromine. So bromine will leave with what charge? Negative. And between those two carbons, where will the positive charge be? The secondary one. And then what did I just add right here? Hydrogen. Now you can show that hydrogen if you want. Okay. I don't want to either. Too lazy. So what is my last step? Bromine will do what? Yeah, make a bond to that carbocation carbon, giving me this. Any questions about that? We'll call it the addition of HX. And I'm calling it HX because X could be any of the halogens. So a hydrogen and a halogen. There's not like a name per se, like a scientist's name for it. Like, yeah, I should name it after myself. All right, and those are the two reactions we learned yesterday. Okay, let's see what the next one is. Hydration. Okay, this one is a hydration. So when you think of hydration, what do you think of? Water. So what do you think I'm going to add across this double bond? Water. So let's think of like H2O. But I'm going to draw it like this. Okay? The one we just did, not this one, but the one before that, what did we add across the double bond? Hydrogen and a halogen. Okay? Do you see if I write this kind of like this, it's going to add a hydrogen and an OH, an alcohol. And when I combine those, that makes water. So water will be added, but it's going to be in the form of hydrogen on one side, alcohol on the other side. But let's look what we have here. This is a hydronium. This is an acid. Let me draw it like this. What does an acid do? Gives up a hydrogen. So just like the mechanism we just did before, what do you think the first step is? Double bond grabs a hydrogen. And where do you think that hydrogen goes? Or let me ask this. So is there any peroxide in this? So what do you think this is? Makarnikov or anti-Makarnikov? Makarnikov? So where will the positive charge go? Which one would be more stable, primary or secondary? Secondary. So I have the positive on the secondary, so that means I added the hydrogen where? On the primary. And I'm going to go ahead and draw that hydrogen in just so you can see it. And there's two others there. And so this was H3O plus, so what does it leave as after the hydrogen was H2O? And let me give you the final product here. Depends on what question I'm asking you. If it's a mechanism like we're doing right now, yes, you would get this. If it was to predict the product, then no. Yeah, mechanism, you'll always get the full reaction. So you can see where things are added and use that to your advantage. Okay? So what do I need to add right here? Look at our product. The alcohol. Where do you think that comes from? The water. So let's add our oxygen to there. See what we make. Okay. So do you see that I added my water there? Why does it have a positive charge? Yeah, 2 so it has, it's not using enough valence electrons. So the formal charge is positive. Now let's look at our final product. We're pretty close to that, right? What do I need to do from here to here? Just take a hydrogen off. Now this is where you're going to use, we always joke and call it magic water. Which leg? Here? That's just coming off that carbon. There's 3 of them. I'm just showing the one I added. So that's just a bond, a hydrogen bond coming off that carbon. Okay, this water comes from H0+. So H0+ is kind of like an equilibrium. Going back and forth. Anyway, anytime you see H0+, that means there's a lot of water in there too. Okay? So it's like acidic water. Okay, so, and think about when you make yourself a glass of water, is there only one water molecule in there? No, there's like countless, numerous, billions, trillions of water molecules. Okay? So these water molecules, it looks like I'm making it come out of nowhere, but just know it's just in solution. Okay? Anytime you see H0+, there's as many water molecules as you need to make up. Yes? Usually heavy water, they're looking at like with deuterium and stuff. So like D2O or something. So what is this water going to do? What does it need to get to here? Take a hydrogen off. Hydrogen leaves its electrons on oxygen. And then do you see here, when I grab that hydrogen off, H2O will become what? H3O. And you see how I wrote H3O plus over here? So you regenerate your acid. Oh, here. It's magic. It's just in solution. We don't really balance equations. If we need a water molecule, we just have it sort of appear. So this is very, very similar to the mechanism we did before. Let's look at it. So the first step, we grab a hydrogen off, okay, which adds the hydrogen, forms the carbocation, just like the other mechanism. Then in here, our nucleophile, before we had a halogen, and in this case it's water. Water comes and makes a bond to the positive charge. So now it's on there. Now, the only difference between this one and adding a halogen is we have to have that extra step of taking off that hydrogen. Did we have to take a hydrogen off with like a chlorine? No, because it only had one hydrogen anyways. So we didn't have to do this extra step here. But from here to here is the same exact mechanism, except instead of like chlorine or bromine right here attacking, we have water attacking instead. So again, it's good to see where they're similar, so you're not just memorizing like all these individual things. If you see that, okay, well this mechanism is almost identical to the other one, I mean, you just, cut your studying time by maybe 10 minutes. But that's 10 minutes that you could do something else. Yeah, or sleep. Do you see that we form a carbocation here? Remember, anytime you form a carbocation, it can rearrange. Do we like rearrangements? No, we don't. Because then we don't know what we're going to make, because it rearranges possibly into something completely different. Plus, it makes the mechanism harder. So rearrangements are bad. Okay? So we would like to have, so the HCl, HBr, all of those, there's no other way to do those. But with water, there's two other reactions we can use that'll have no rearrangements. Okay? Now, this one's easy to do in the lab and cheap. Okay? You just put acidic water, in your reaction with your double bond and heat it up, and it'll add that. The only problem is you get rearrangements. So it's cheap, easy, the possible rearrangements. So they have another way to do this reaction. So you don't have to worry about rearrangements. It's a lot more predictable. So before we do that one, let's practice one more time doing this. Let's do a predict the product. So how do I know what I'm going to add across the double bond? What tells me? Yeah, well, not hydrogen peroxide, but the hydrogen, the H0+. The double bond doesn't tell me anything because every reaction we're going to do in here will have a double bond. Okay? But what is over the arrow tells you which reaction you're going to do. So if I had HCl over the arrow, do you see that would give me a different product than putting H0+? So if I have H0+, what am I adding across the double bond? An H and a OH. So where will the OH go? That's the most important one. That's the bottom. The top one. Is there hydrogen peroxide in here? No. So is that Makar-Markov or anti? Makar-Markov. So then let's look at both of these. This is what degree carbon? Tertiary. And this one would be secondary. So where would the carbocation prefer to go? Tertiary, which is where your OH will go. Think of your OH as similar to like your chlorine or your bromine. So it's really, you're looking at what's the position of the non-hydrogen. Like without the double bond. Yeah. Think of it like over here. Okay, and if I wanted to add a bromine there instead, what would I have put over the arrow? HBr. And if I wanted to add a chlorine to the lowest degree carbon, what would I put in there? HCl, H2O2. Okay, because I get the question a lot, how do I know what to put on here? How do I know it's not a chlorine? How do I know it's the alcohol? It's this right here. And literally, it's memorization. I mean, there's no other way around it. You make your flashcards, make your list, however you want to do it. But there's definitely some memorization in this class. I mean, anything you do, there's memorization. So how you know is by what's over the arrow. That tells you. And you just have to memorize each reaction individually. And it'll come quicker. I mean, we've only learned 3 so far, but it's not too bad. Now, the next 2 we're about to do, what comes over the arrow is like a little bit crazy. It's not as pretty as these. So let me show you this. I'm going to put the same reaction. So this is a brand new one. There you go. OAC, so that's O acetic, and so that group looks like this, bonded to mercury. Oh, like acetyl. It's an acetyl group bonded to an oxygen. This is that group. OAC. A. So it's OAC. OAC. These groups, these branches are on the mercury just to stabilize it so it's not as reactive. I mean, mercury's going to be reactive despite that, but it's just there to, so it just doesn't go crazy. So they're just stabilizing branches. That's their only role. Okay, but do you see this over the arrow just got a little crazier? Like, what did I just do, you know? And so you might think in your head, oh my goodness, do I need to memorize all of this for the synthesis? Yes, you do. That is the answer. So if, I'll give you the product here in a second, but if this is the answer, you have to give me all of this. So whatever I write above, below the arrow, that's exactly what you have to write to get the answer correct. Okay? And we'll go over how this works. Don't worry about the side products. But that's what it'll give you. Synthesis? Yeah. This here. Yeah. You don't have to draw this. You just have to know that it just abbreviate it. Acid, it's oxygen, acid, OAC is all you have to put there. No, I mean, it's this group right here, but you don't really know what that group is right now. You'll know it in organic too. So just know that mercury is bonded to OAC, which is, all they do is stabilize. That's it. That's all you need to know at this point. All right, look at the above reaction. Do the products look similar? I mean, actually identical? And let's look at the starting material. Is that identical? What's the only difference? What's over the arrow? These 2 reactions give you the same exact product. So you might ask, why would we have both?
Why would we have both?
Good question. It's because this one could rearrange. Do we like rearrangements?
No.
No. This one does not rearrange. Is that better? Yes. This one gives you like the exact price. This one's cheaper, but you can have a lot of problems with this. Not only can it rearrange, but since it can rearrange, you'll end up with multiple products, and it can be a nightmare. This will only give you one product, which is nice. So let's look at this, how this happens. The first part of the reaction, and you don't need to actually know this mechanism. Okay, you'll have to know why there's not rearrangements, maybe explain it to me. But you don't actually have to draw the mechanism. But I do want to show you a little bit so it makes sense. So what happens here is the double bond is going to attack the mercury, just like it was going to do with like a hydrogen. And then at the same exact time, mercury is going to come back around and attack the double bond. So they attack each other at the same time. So if I draw an arrow like this pointing at mercury, what does that mean? What did I just make there? A bond. And then I have an arrow drawn right there, so what did I just make? Another bond. Exactly. Now you'll remember it. Maybe. So do you see what I have drawn here is mercury bonded to each side of the double bond. So do you see that there's no carbocation there? There's a positive on the mercury, but that doesn't matter. There's lone pairs on it. Okay, so do you see mercury takes up both spaces on the double bond? So there's no carbocation formed. That's why it doesn't rearrange, because mercury just basically is a placeholder for both positions. And that's the point of putting this mercury species in there, is so you do not have a carbocation. It takes up both spaces, so nothing will happen. So that's why. So if I ask you to explain why there's not a carbocation, it's because mercury will make a bond to both carbons on the double bond. So no carbocation is formed. Mercury forms a bond to both, we'll say, alkene carbons, I mean the double bond carbons. So no carbocation is formed. Yeah, it does on the mercury, but not a carbocation, which is a carbon with a positive charge. So it does form a cation, but not a carbocation. Yeah, but like explain why. So the mercury takes up both positions, and it doesn't matter that it forms a cation. But the thing is, it doesn't form a carbocation. All right, now let's look here. I need to, so do you see step 1? We do step 1 first. So there's step 1, step 2. So I just used the mercury. So what else do I need to use in here? H2O. So the water is going to come in, and it's the oxygen that's going to bond. And let's look at our product. Where does that oxygen bond? We'll say the top or the bottom? The top. So it's going to come over here, make a bond. And look at this carbon. How many bonds does it have already? 4. So can I just do that? No. So what happens is one of the bonds to mercury breaks. There, and then let me just do this step really quick, because again, it's not a mechanism you need to know. So just, do you see that it added as water, but in the final product, what is it? OH. So we're just going to use one of our magic waters again and just take off one of the hydrogens. Okay, let's look at this. I have my OH on there, and my final product is the mercury on there. No, do we agree we want to get rid of the mercury? Okay, so do you see in step 2 I have NaBH4 on step 2? This is called sodium borohydride, and this, once it gets into solution, so once you put it in the reaction, what it does, it releases, the most important thing it does, it releases what's called a hydride. Like this. So this turns, basically this will turn into that. There's going to be some byproducts, but NaBH4 turns into a hydride. And what this does is going to make a bond right here where this mercury is and make it leave to form your final product. Now again, that's not a mechanism you actually, I won't make you reproduce this on the exam, but I want you to kind of understand what's going on here. So like, what is the point of all of these different things in there? So why do we put mercury in there? Yeah, so you don't have a carbocation. There's no rearrangements, nothing. Why is there water? Yeah, to make, well, yeah, to take off a hydrogen or magic water, but also that's what we're adding the alcohol. Okay, so that alcohol on here, that OH, comes from water. Why do we have NaBH4 in there? Take the mercury off. Water forms alcohol. So that's why we have all three of those in there. They all have their own function. So mercury, no carbocation, adds the OH, takes off the mercury. Okay, and then was this Makarnikov or anti-Makarnikov? Makarnikov. What would be on the arrow or below it if it was anti? H2O2. One other thing to know about this reaction, it adds what we call anti, meaning, let me go ahead and draw that hydrogen in. So if this OH, let's just say that it added on a wedge, so it came from the front. If I tell you this is anti-addition, where do you think the hydrogen came from? So that's a wedge, so this would be a dash. They're always going to add anti or trans-like. The reason is, so the OH, the water comes in here, which is fine. But do you see that this is like an SN2? So your nucleophile comes in, leaving group leaves. Okay? So just a quick SN2. Remember, you have inversion when you do an SN2. So if the water came from the front, the hydrogen will come from the opposite side. Anyway, so long story short, this will always be an anti-addition. That doesn't mean anything about anti-Makarnikov, just anti or trans. So usually on the predict the product, I'll say show, predict the product and show stereochemistry when necessary. So anytime I show you wedges and dashes and I tell you something like that, those are the reactions you need to show it to me. Have we done this before on any of the reactions? have I showed you like a wedge and a dash? On any of no, not yet. So this is the first one that this matters. The other ones, I mean, sometimes they're wedge, sometimes they're dash. They don't matter, but this one does. And if I show you, hopefully I didn't. And I probably did. Nope, it's there. Okay, do you see here's the mercury, the water, NaBH4. Do you see that I actually explicitly draw wedges and dashes on here? Did I draw them anywhere over here? No, because they don't matter. And then I also put on here that it cut off a little bit, anti-HOH. So these are always going to be, if one's on a wedge, is on a dash. Now it doesn't matter which one's which. Okay, so here I think I have the dash as the OH and the H as a wedge. It doesn't matter. That, 50-50 chance there. But the point is that they're always going to add opposite of each other. So you don't have to memorize one or the other on the exam. It's just they're going to be different. So I have this on there. So again, unless I show you wedges and dashes, it doesn't matter. So do you see the next two reactions? You see some wedges and dashes on there? So those will matter, but the three we did above that won't. Okay, so go back over here. So we had the one with H3O plus, and what did that add across the double bond? H and OH, Makarnikov or anti-Makarnikov? Makarnikov, because there's no peroxide in there. And what was wrong with this one? Why did we want another way to do it? Rearrange. So then we had it, here it is, the mercury with the water and the NaBH4. So let's review this again. Why do we put mercury in there? No rearrangements. Why is the water in there? Make the OH, the alcohol. Why is the NaBH4 in there? To get rid of the H. This reaction, I don't quiz you over the names of them, but if you like to know the names of them, it's called an oxymercuration demercuration. NaBH4 takes off the mercury. Yes. Can I do what? H3O plus, that one's just called a hydration. And the one with the mercury is called an oxymercuration demercuration. You don't have to actually know the names of them, but if it helps. Oh, the mercury. Oh, the mercury makes it where there's no carbocation formed. So it can't rearrange. So you look on here, we're going to mercurate it, meaning we're going to add mercury. And then what does demercuration mean? Take it off. So that's where the name comes from. Oxy is just because it has the oxygen, the acetate groups on there. Okay, so let's look at one more before we take a break. So if we have one where we add an alcohol, which is OH, Makarnikov, what's the one we haven't seen yet? OH adding anti-Makarnikov. This goes on forever. And they're still doing it. Okay, this is called a hydroboration. Hydro meaning like water, boration meaning boron. And let me give you the product of this one. And let me go ahead and draw. This. Love you. Okay, so this is antimicrobial, but how would you know that? Yeah, the hydrogen peroxide right here. So the OH, or your non-hydrogen, added to the least substituted carbon, the lower degree carbon. Now, this is not a mechanism you need to know either, but let me kind of explain really quick what happens here. Let me see if I have a picture of it, because it would be better than what I can draw if I have one. Here it is. Okay. So your BH3, do you see they draw it like this, BH2 with a hydrogen, which is BH3, okay? Now what happens, they show it like this, because you see right here, what happens, you get this sort of transition state where the hydrogen, one of the hydrogens from the boron, will be added to one carbon from the alkene, and then the remaining BH2 will be added to the other side. And this happens at the same time. It literally almost like lifts itself up. So one of the hydrogens adds to one carbon, the boron adds to the other one. So do you see here? It's no longer BH3, it's H on one side, BH2 on the other side. So do you see that it added on the same side here? Anyway. Then we have our OH. Right here. We'll just come in and knock the boron off. And these prefer, mainly because of the boron, will actually end up adding on the same side. So that's what we call that when they're both like a wedge, or we could have put both a dash. We call that syn. Or if you want, it's kind of like a cis, right? So you either could put both wedges or both dashes, just as long as they're the same. So let's look at what's the point of, there's actually really 2 points of this BH3. Can you think of the two? One is that it adds a hydrogen. Adds a hydrogen to one side, which is this side here. So BH3, one thing it does is it adds a hydrogen. Did we form a carbocation here? No. So that's the other thing it does. So one side it adds a hydrogen to, the other side it bonds to, so no carbocation is formed. So we'll say like allows no, I'm going to put C plus for carbocation formed. Why did I abbreviate that as C plus? Make sure you understand that. What is a carbocation? A positively charged carbon, so C plus. So it allows for no carbocation to be formed because it takes up where it would have been. And then what's the point of the hydroxide here, the OH? That's where it gets rid of the BH3 and it adds as the alcohol there. And what is the point of the peroxide? To make it antimicrobial. So that's the point of all of them. So if I want to add a chlorine to the least substituted side, to the lower degree carbon, what do I put in there? HCl and, H2O2. What if I want to add alcohol on there, Makarnikov, okay? But I could care less if there are rearrangements or not. So there's really two choices. H3O plus is one choice, and what's the other one? Oh, what's another way? Yeah, the mercury water with the NaBH4. And then if I want to do it anti-Makarnikov, what's the only way to do it? BH3OH, H2O2. Adding H3O plus with peroxide will not make an anti-Makarnikov. So this is the only way to do anti-Makarnikov addition of OH. All right, let's take a break, and then we'll get back to work. All right, let's go ahead and start back up. Okay, let me see the next reaction. Let me see how far I want to go. All right, let's just learn 3 more reactions today, and then we'll be done. Okay? 3 more. 3 more. Okay, so let's look at this one. This one's pretty simple to predict. Okay, now based on your knowledge of the reactions we've done so far, what do you think adds across the double bond? A Br and a Br. So 2 bromines. Do you think it matters where you put either one? No, so there's not really a Makar-Markov or an anti-Makar-Markov. I guess if you want to call it Makar-Markov, that's fine. But we're adding 2 bromines. So it doesn't matter if we add this one here or there. Bromine's bromine. So we're going to add 1 bromine on one side, another bromine on the other side. Now these are larger groups, so do things like to be crowded? No, so how do you think these would add, meaning like looking at wedges and dashes? What? Yeah, they're opposite. So if one's dash, the other would be wedge. Or you could put wedge dash, but they're going to be opposite. So this is the anti or trans. Okay, and what indicates that I add 2 bromines across the double bond? The 2 bromines on the arrow. Is there anything on this arrow above or below it? No, so it's the only 2 things you can add. Remember, we're always going to add 2 things across the double bond. And if you can't see one of them, it's because it's a hydrogen. So let me show you this mechanism. This is a mechanism you do need to know. There's no rearrangements in this. So do you think I'm going to form a carbocation? No. So this mechanism is very similar to the mercury one. So this double bond will make let's say, attack the bromine. And then what do you think the bromine does? Attacks it right back. So what do I form right there? What will that look like? Kind of like a triangle, sort of. So bromine, and then this bond will break, sorry. What? Here? What about it? Yeah, it's between the 2. So it makes a bond to both sides, which kind of forms like a triangle. All right, now remember when we're doing a mechanism, we always quote unquote cheat and look at the product. Okay? How many bromines on the product? 2. How many do we have on there right now? 1. So what do you think happens? Yeah, bromine has a negative charge, and it's going to attack. It doesn't actually matter which carbon here, because it's kind of 50-50 which one it's going to make a bond to. So let's say it makes a bond right there, which causes that bond to break and open up to bromine. So let's think, and that gives you your final product, but let's think about this. Yes, yes. So it's kind of like a triangle with a bromine on top. Okay, so when I made this line, let's see this arrow line, right there, what did I just make? A bond. Okay, so I'm going to make a bond to bromine. Now when this one moved to the bromine, what did it become? Oh, where did these electrons move to? Bromine as a lone pair. Good. Okay. So is it there? Is this bond there anymore? No. So if you kind of like, I can't. Without. So that's not there. So do you see this bromine now is only connected down here? Did I do anything with this bond? No, it's still there. So there's still a bromine connected there. It was connected like that. Okay? And that other bromine right here just made a bond right there. Now, bromine's large, so let's just pretend if these are both wedges. It could be whatever. Then this bromine will want to come in on the opposite side, kind of like an SN2. So it's this will always come in the opposite side of what like the bromine is. Meaning if this is going forward, it's going to come in from the back. So you'll always get a wedge and a dash. Any questions about this one? Now we're going to do one that's very, very similar. But we're going to change one thing. So I'm going to flip this page. Okay, let's see what we have here. Let's look at our product. We added a bromine and an alcohol on here. Where did the bromine come from? The BRBR. And where did the alcohol come from? The water. This mechanism is going to start off exactly the same. So what's the first thing that happens? The double bond will do what? Go to the Br, and at the same time, bromine goes to the double bond. And then what happens with this bond here? Go to the Br and break. And what will this look like, this little crazy arrow thing I have here? Like a triangle. And then this bromine here will leave with what charge? Negative. Which one leaves? Yeah. Okay, now if we only had bromine in there, what would have happened? This would have done what? It would have made a bond right there, and that would have opened. Correct? But let's look. Is that what happens? What attacks there instead? Water. And let me tell you why. And, well, let me draw these arrows first. So it's going to be exactly the same. So it's going to attack there, causing that bond to open up. The reason water attacks is two reasons. One, oxygen is a better nucleophile. It's further to the left. But more important is that you put a ton of water in there. Okay? So let's say I have, this beaker, and I put in, 2 milliliters of bromine, Br2. Okay? And then what I do is I'll put in maybe 50 milliliters of water. Okay? Maybe more. But do you see I have so much more water than I do bromine? It overwhelms the bromine so that water gets a chance to attack. So they put in, 20 times the amount of water, whatever, 10 to 20 times the amount, to make sure that water attacks. Now, does some of this bromine attack here instead? Of course, probably a little bit. But they put in so much water that the majority of it, your major product, will be this. So let's see what happens. How is this bonded? So this bond just broke and became what? A lone pair. So is it bonded right there anymore? No. So we have here, here. Bromine is just going to be bonded on this side. And then what's over here? H2O. What is my final step? What do I need to do? Yeah, the bromine is going to take off a hydrogen on the water. You see we form the HBr. Now, just like the one we just did, how do you think this will add? So let's say this is a wedge. So the bromine would be a dash. These are almost identical reactions. So these mechanisms, think of them as almost the same thing. Because you see the bromine comes in here, makes this sort of triangle cation. And the only difference is the reaction before, bromine attacked there, because we didn't have any water in there. But on this one instead of bromine attacking, we just have water attacking. Okay, so it's just, do you have bromine or do you have water attacking? But the arrows are exactly the same. How do we know when we have water attacking? It's in the product, but it's also one of the ingredients, if you want. It's added in there. The other one, did I have water listed above or below it? No. So if water is listed as one of your chemicals you're using, okay, then you're going to have the OH on there. This is, for predictive product reasons. So it's basically, is there water there or not? If there is water there, you will add an OH. If there is not water there, it'll just be 2 bromines. I think either this is the last mechanism or you might have one more. And that's it for the whole chapter, okay? Because I know the mechanisms are usually the hardest part. So one more reaction I want to show you today, and then I'll let you out early because I know reactions can just be a lot. There's a lot of info. And you start to kind of go brain dead. And this is an easy one. I left this the last one for a reason. Okay, so this palladium at the bottom, the only reason it's in there is because it's a catalyst. Does anybody know, is a catalyst actually like part of the reaction? Like, will it end up in the product? No. It just helps the reaction go, if you want. So the palladium will play no role in the product except helping you form it, okay? So if you want, for right now, write it on there, but we're going to try to predict the product using our knowledge. What do I have here? 2 hydrogens. So what do you think I add across the double bond? 2 hydrogens, right? Do I show my hydrogens? No, so do you see it'll just look like that. So over here I have an alkene, meaning a double bond. And then what did it just turn into? An alkane. So basically it like erases the double bond, if you want. Simple enough, right? Not too bad. So if I have if I just have Br2 and this here, what would I add across the double bond? 2 bromines. What if I had bromine with water? OH and Br. What if I had mercury, water, and a BH4? OH and H? And is that Makarnikov or anti-Makarnikov? There's no peroxide in it. Then Makarnikov. What if I put BH3, OH minus, and H2O2? Anti-Makarnikov. Do you remember what I add? H and OH. So it's the anti-Makarnikov version of the alcohol. What if I have HCl? H and Cl, and how do I make that anti-Makarnikov? Add peroxide. And then what if what would H3O plus add in there? Water. So H and OH, and would that be Makarnikov or anti-Makarnikov? Makarnikov. And again, how do I know if something's going to be Makarnikov or anti? What do I look for? Peroxide. And peroxide tells me which one? Anti-Makarnikov. H2O2. What about bulky? No, that's for elimination. Different chapter. Forget you even thought it. What does it look like? Or you could write it HOOH, or sometimes ROOR. 2 oxygens bonded together is a peroxide. It's a peroxide. This is specifically hydrogen peroxide. This stands for any peroxide. So that's it for today. So what I would recommend, obviously I can't put a gun to your head and force you to do this, but go home and either make a list or note cards, however you want to study, of the reactions we just learned. And then also go home and write up each of these mechanisms, maybe like 3 times each, okay? And I promise you, if you do that, it'll save you a lot of headaches tomorrow and Thursday, okay? So just take 30, 45 minutes to kind of go over the material, and that'll help you. That's okay.